Welcome to the class of managerial economics. Today we will discuss the regression analysis approach to demand estimation. Going into the background of the approach, we know that there are two methods to demand estimation. One is the marketing research approach, and the other is a regression analysis approach. The marketing research approaches are quite theoretical type of qualitative type of approach in which we discussed in the last class the consumer clinics, the consumer surveys, the observational research, and the market experiments. Today we will discuss the regression analysis approach to demand estimation. This approach is a little quantitative. It is a quantitative approach to demand estimation, and it involves some of the econometric techniques to understand. So let us start. Suppose that the manager of a firm is interested in finding out the impact of the advertisement expenditure on sales. He want to find the effect of the advertisement expenditure on sales. He is interested in increasing the sales. So one idea in his mind is that if the firm increase the expenditure on advertisement, will sales increase? So in order to find out the relationship, he collects 10 years of the data, 10 years of the observation sales, as we see in this table. Now he takes sales as a dependent. We know that he takes sales as a dependent variable, while the advertisement expenditure as independent variable, because it is usually expected that if the advertisement expenditure is increased, what will happen that it will lead to increase the sales. So suppose we denote the sales by Y and the advertisement expenditure by X. We know that usually the dependent variable is denoted by Y. So we suppose that the sales are denoted by Y, while the advertisement expenditure is represented by X. The data is shown in this table. The data is shown in this table. In the figures in this figure, this diagram, this is actually called this is called the scatter diagram. The figure is called scatter diagram. Now what the manager will do, that these are actually X, which shows the advertisement expenditure. This is Y, the sales. Means that in the year one, the 10 years are spent on advertisement, it leads to 44 of the out sales. If 9, it is 40. If it is 11, it is 42. If 12, and these are the different observations of the advertisement expenditure, and these are the different advertisement expenditure on which have been represented by Y. Now, in order to show the relationship, find the relationship between the sales and the advertisement expenditure, he plots it on the graph. We see in this graph that the advertisement expenditure, which is independent variable, explanative variable, it has been taken on x-axis. Similarly, the sales dependent variable has been taken on y-axis. Now suppose we take the first pair, 10 of x and 44 of y. So this is 10 of x, 44 of y, the first observation. 10 and 44. This is 10 of x, 44 of y. Similarly, the next observation is 9 of x and 40 of y. 9 of x, this is 9 of x, and 40 of y. Similarly, this point shows this 11 of x and 42 of y. This point shows 12 of x and 46 of y. This 12 of x and 46 of y. Means that in this, you know that these are ordered pair. The first observation shows x and the second shows y. Similarly, this point shows 13 of x and 58 of y. So we can draw all these observations, this x and this y, this x and this y, this x and this y, this x and this y on the graph, and we will get these different points as we see in this diagram. But looking at the diagram, we see that there seems a positive relationship between the y and the x. Means looking at this diagram, one can predict that by increasing the advertisement expenditure, what will happen to the sales? Sales will also increase. So this gives us an idea, a sketch of the relationship between the advertisement expenditure and the sales. We can read it from the slide. Now the points show visually a positive relationship between x and y. Means that if x increases, what will happen to? If x increases, y increases. If x further increases, y further increases. If x further increases, we see a rise in the y. We can extend it to further observations too, but it is difficult to estimate from the figure, this figure, that how much of sales are increased by how much of advertisement expenditure. We can extend it to other observations. We can take further observations, but what the problem is that this analysis will not be able to help us in finding out how much increase in the advertisement expenditure will lead to how much increase in the sales. Similarly, what the problem with this is that possibly different researchers may draw different results from this type of the scatter diagram, because this someone can draw it this way, these, and this way. Then it will show no relationship between x and y. Similarly, different people can draw different results from conclusions from this diagram. So the scatter diagram is sometimes not very useful. It gives us a direction, but not very useful. So what we do in order to overcome this difficulty, we make use of regression, a very simple technique. Now, what is the regression? Regression is a statistical technique for obtaining the line that best fits the data points according to an objective statistical criterion, so that all researchers looking at this data would get exactly the same result. So in simple word, what is regression? Regression is actually a statistical technique, and it helps us in getting a line which best fits the data. We do it econometrically by use of mathematical and statistical tools, not drawing this line through on a graph, but by deriving the line statistically. A regression analysis is the study of how a response variable depends on one or more predictors. It lets us know how the dependent variable reacts to changes in the independent variables. Similarly, another definition is regression analysis is a set of statistical processes for estimating the relationship between dependent variable and one or more independent variables. We discussed it in the coming classes, in the coming slides, that it is actually the regression analysis tells us the relationship between a dependent variable, which is usually mostly denoted by y, and one or more independent variables. Similarly, another definition given by another economist is that regression analysis is the study of relationship between two or more variables and is usually conducted for the following reasons. Why we conduct the regression analysis? We conduct the regression analysis for these reasons. So the regression analysis is conducted for these variables, which you know that the regression analysis is actually the study of relationship between two or more variables, and it is conducted in order to find the relationship between two or more variables, whether the relationship exists. Similarly, when we are interested in understanding the nature of relationship between two or more variables, and when we want to predict a variable given the values of others. It is also used for prediction. It is used for finding the impact of one variable on other variable, or to find the determinants of a dependent variable, and the determinants can be, which are usually known as explanatory variables or dependent variables, and can be one or more than one. The regression line can be obtained by minimizing the sum of square of residuals. The method is therefore called the method of ordinary least squares. There are two types of the regression. One is a simple regression, and we say that we have, in the simple regression, we have one dependent variable, a dependent variable, and one independent variables, or the regression of two variables, in which we, as we see in this simple example, as there is one independent variable, such type of the regression is called simple linear regression. This is the functional form of the data, and we can transform it to mathematical form, where we have the yt is equal to a plus bxt plus et. This is a simple linear regression line. This line is known as simple linear regression line. You may have read about the equation for the straight line, which is a plus bx. This has been derived from the concept of that, and this ei is a residual or the error term. Remember that this error term has a few assumptions which are very, very important to remember, because if any of these assumption is violated, it will lead to misleading results. It will create problems in the estimation of the regression results. When we take it estimated form, we get y hat is equal to a hat plus b hat xt. Now, what is the residual? Residual or error is actually the difference between the actual and the estimated value. The difference between actual and estimated value is called the error or the residual. So we can get the estimates of parameters a and b by minimizing the sum of square of residuals. If we square it, yes, e square, this is square of residual, and when we sum it, this is the sum of square of residual, and we know that et is equal to yt minus yt hat square, or by putting the value of this yt, we get yt minus a hat minus b hat xt whole square. Now we can minimize it, and you know that for minimization we make use of the partial derivatives. So if you take the partial derivative of this equation and with respect to a and b, and then simplify it, we will be able to get the value for the formula for the b hat, the slope of the line. Here in this line, this a is the intercept and b is the slope. So if we minimize this sum of square of this residuals, means if you take its partial derivative with respect to first a, as there are two, we are taking it with respect to b, a and b. So first we take the derivative with respect to a, where we will assume the value of b as constant, and while differentiating with respect to b, we will take a constant, and after simplification we get a formula for the b hat as the sum of x minus x bar into y minus y bar divided by the sum of x minus x bar whole square. You should remember this formula. I am not going into the detail of the derivation of this formula because this is not part of your course. It is just to give you an idea that this formula has been derived through this process. Similarly, once we derive this formula, we can also derive the formula for the intercept y bar minus b hat x bar. Now, if you are asked, we have this example of that the same, the manager's data, the time or the number of observations and 10 observations. This is the x value t, and this is the y, x minus x bar, y minus y bar, and so on. First of all, we sum the x. The sum is 120. So the sum of x is 120. We can see it here. The sum of y is 500. If we add all these observations of y, we get 500. So the sum of y is 500. Observations are 10. So n is 10. Now, we as per formula, we have to find the x minus x bar and y minus bar as well. So for this, we need the value of the x bar and the value of y bar. So now, how to calculate the x bar and y bar? For the x bar, we have the formula, statistical formula. You know that summation x over n, and this is actually summation x over n, not summation x by n. The sum of x by, this is summation x. There are some typing issue that this is the sum of x by n. So the sum of x here is 120, or by n 10 we get 12. Similarly, the y bar is the summation y by n. Remember, dear students, that this is actually the sum of y by n, not the sum of y by n, but this is actually the sum of y by n. Some typing mistake. So the sum of y is 500 divided by n is 10. So we get the y bar 50. We got the x bar here 50. So after finding the x bar and y bar, we calculate the x minus x bar column. It is very simple. We just subtract x bar from each value of x. Now we have x bar as 12, this 12. So we subtract 12 from this whole column. 10 minus 2, 10 minus 12 minus 2, 9 minus 10, we get 3. 11 minus 12, we get minus 1. 12 minus 12, we get 0. 11 minus 12 minus 1, 12 minus 12, 0, and so on. So subtract x bar from each value of the x. We will get a corresponding value in this column x minus x bar. Similarly, for y minus y bar, we subtract y bar from each of the y values. Now we have y bar as 50. So 44 minus 50 minus 6. 40 minus 50 minus 10, 42 minus 50, it is 8 minus 8, and so on. So we get this this column y minus bar by subtracting y bar from each of the y values. Now this column is actually the multiplication of this and this, x minus x bar into y minus y bar. X minus x bar is 2, 2 into minus 6, we get 12. Minus 3 into minus 10, we get minus minus plus, 3 tens are 30. Minus minus plus, 8 ones are 8. 0 into minus 4, 0. Minus 2, 1 into minus 2, 2, and so on. The last column is x minus x bar whole square. We take this square of this x minus x bar column. 2 square 4, the square of 3 9, square of minus 1 1, square of 0 0, square of minus 1 1, and so on. And then we add this column vertically and this column. The sum of this column is which is actually the sum of x minus x bar into y minus y bar. This is 106, and the sum of x minus x bar whole square is 3. We have written here the sum of x into x bar minus y minus x bar is 106. This one. Why sum of x minus x bar whole square is 30. This is sum of x minus x bar whole square is 30. Now it is not difficult to find the value of the b hat. We know that the formula for b hat is this one, and we can copy it from here. Let's suppose for the yes, if we can put it here, so that you may remember it. I put the formula here. Yes, I think it's okay. Yeah, it's okay now. Yes. So the sum of x minus x bar whole square, this is the 106. Sum of x minus x bar whole square, this is sum of x minus x bar into y minus y bar. This is 106. Yes. The sum of x minus x bar whole square, sum of x minus x bar whole square is 30. So we get b hat as 3.35, which is actually the slope of the line. And for the intercept, we put the values in the formula, this formula. You can also copy this here. So this is actually y bar. We know that y bar is 50 minus b hat, it is 3.53 into x bar is 12. So by multiplication and subtracting it from 50, we get the value of a is 7.60. So this is actually we can put it in the regression line as well. We if you want to write the estimated regression line, this will be we can write it. Let me write it. Y is equal to, we had the yes. So B naught is a bar is 7.6. We get 7.6 plus 3.53, if I'm not wrong, 3.53 and xt. So this is the estimated regression line. This is the b hat, y hat is equal to 7.6 plus 3.53 xt3. The slope is a positive. We see here that the slope is positive, means that if the advertisement expenditure increases, it will increase the sales, because we know that this is actually the sales. Y shows the sales, so the positive the sign shows the positive relationship between the y and x, and if there is a 1 unit change in the x, it will bring about 3.53 point change in the y. So this means that the manager should increase the sales, the advertisement expenditure, in order to increase the sales. Similarly, dear students, now coming to another example. This is a practice for you. You can do it at your home. Here we have income and expenditure relationship. This is expenditure on food, actually. Expenditure on food. Given the following income and food expenditure data, estimate the regression line of food expenditure on income and interpret your result. Explain your result. Explain the type of the relationship. By here we know that now this is your homework. You can, as an assignment, that we know that the advertisement expenditure depends on income. So food expenditure depends on income. The more the income, the more the food expenditure. So food expenditure is dependent variable here, and income is the independent variable here. So you can use this method as we explained in this example 1 to find the values of the A and B for this regression line. So it is your assignment. Dear students, after computing the values of A and B, the slope and intercept, there are some type of the tests of significance for it, some statistical tests which are known as tests of significance. We use different types of tests for finding the tests of significance, like the z-test, like the t-test. We have t-test, we have z-test. Similarly, we have also the standard error test. These are different types of the tests which are used by econometrician to find the significance of the parameters A and B, which we derived in the previous slides. So the procedure for the this test is not difficult. It is actually consists of a few steps. If you remember these steps and you just understand these, so it will not be difficult to conduct the test of significance. We first usually the test which is by default used, we do let us discuss the procedure for the t-test. In this test, first of all, the first step is the statement of hypothesis, where we state the null and alternative hypothesis. The second step becomes the level of significance. We know that the level of significance is denoted by alpha, and the level of significance we take different 0.01, 0.05, etc. These are different levels of significance which are usually used for finding the test of significance. The third step is the test statistic. It is actually the formula for the t. For example, in this example, we have this t formula behaved by this one. Now this formula, this is in this step we just write the formula. In the fourth step is important one, where we find the critical region. This is actually the region where the value of the t will fall out of it. We can derive the critical region from the t table. We have the student t table. You can find the values of the different sample size there, and then we make the calculations, and at the end we draw the conclusion. We come to again our example number 1. Recall the example number 1. Yes, this one. In the example number 1, we derived the values of the A and B. Now what the next step is? The next step is to find whether this A and B are statistically significant. So the null hypothesis will for this, we suppose we are conducting the hypothesis for this the slope. So the null hypothesis will be this null hypothesis for this test will be that B naught is not significant, B is not significant, against the alternative B is significant. Level of significance we take 0.05. Test statistic is that formula, this one. The fourth step is the critical region. For the critical region, as we will find the degree of freedom, which is usually n minus k. So the number of observations are 10, and k is the number of parameters. We know that there are two parameters A and B, so 10 minus 2 we get 8. So the critical region, if we check it for the 0.05 level of significance, in the t table its value is 2.306, means it should lie in this plus or minus 2.0306. So coming again to this is the critical region. The fourth step is the calculations. So what we do in the calculations, that we just put the values of the B hat and SB. SB is we can calculate the SB standard error of beta by the use of this formula. We already found the value of summation y minus phi hat In example number 1, here this 30, so we put the form 30 sum of x minus x bar, it was 30, and sum of y minus y bar is 65.46, n minus k 10 minus 2. By computing we get 0.52 as the SB value, and the sum of x minus x bar, that is 30. You can compute it in the previous slides. So the t value is b hat divided by SB, which is equal to 3.53 divided by the SB calculated as 0.52. The value is 6.79. Now we see that this 6.79 is too much bigger than 2.303. Means that if the calculated value is greater than the tabulated value, then we reject the null hypothesis that the intercept, the slope is not or the variable is not significant. So here we as the value is 6.79, which is greater than the critical region 2.306. This means that this value lies in the critical region, and we reject the hypothesis H0 that B is not significant and conclude that B is significant. Dear student, that was the simple linear regression. Similarly, if the number of variables are more than 1, the y can be a function of x1 and x2. A simple example can be that the sales depends on not only in the advertisement expenditure but also on the quality of the product. Let x2 be the quality. So similarly, we can have the multiple regression line becomes this one, y plus a plus bx1 plus cx2 plus ei, or if you have more than two variables, independent variables, we can extend it, generalize it up to n number of observations, variables. So regression technique is a very good technique. We can predict on the basis of the regression analysis, but there are some problems in it as well, in its application. You know that while we were discussing in, let's come back to the simple regression. Yes, here I told you that this E is the random term, error term, and it has different observations. Observation number 1 is that the mean value of this EI in any particular period is 0. The variance of this EI will remain constant. Number 3, it is normal. It is normal distributed with 0 mean and sigma square variance. The explanatory variables are not perfectly correlated. So many and different observations are there. So if any of those assumptions is violated, we can find the problems. One of such problem is multicollinearity. The problem of multicollinearity is very common in the economic variables. Very common in economic variables, the problem of the multicollinearity. If you remember that one of the assumptions of the ordinary least square method is that explanatory variables are not correlated. If this assumption is violated, we can have the problem of multicollinearity. The assumption of this EI is that x1 and x2, the explanatory variable, these will not be correlated. If they are found correlated, then we have the problem of multicollinearity. Again, the assumption of OLS is that x1 and x2, which are explanatory variables, they will not be correlated. But if this x1 and x2 are found correlated, then we have the problem of multicollinearity. In other words, it is a situation when two or more explanatory variables are highly correlated. We suppose that the sales are a function of advertisement expenditure and quality control. And we suppose this advertisement expenditure and quality control are found correlated, then we have the problem of multicollinearity. What this will do, that this will give us very smart t ratios, and it will lead us to misleading results. The solution, therefore, this should be removed. The solution for it, that we should tolerate the existence of multicollinearity if it is not very serious. If it is not creating too much problems, we can tolerate it. Or if it is creating problems but the variable is not very important one, then we can remove that problematic variable. The third suggestion is that we can increase the sample size, which will reduce the multicollinearity. Similarly, we can introduce an additional equation which will also let us reduce the problem of the multicollinearity. Dear students, the next problem associated with the regression analysis is the heteroscedasticity. I'm describing it in simple word because this is not a pure econometric class. So the heteroscedasticity, recall your memory that just a few minutes ago I was describing the assumption of the OLS, and one of the assumption was that the variance of UI, the variance of the error term, the variance of the error term remains constant. This is the assumption of OLS. If this assumption is violated, we have the problem of heteroscedasticity. This is important to note that if the variance is constant, then it means that the model is homoscedastic. In other words, in order to get the reliable results, we should have the homoscedastic model. If it is heteroscedastic, means the variance is not constant, then we have the problem of heteroscedasticity, and it is also often found in the cross-sectional data. It can also create problems for us because it can give us biased standard errors, biased tests, and incorrect confidence intervals. The third problem associated with the regression analysis is the autocorrelation. This is also a violation of one of the assumptions of the OLS. If you remember the assumptions, assumption was that the error terms, consecutive error terms are independent. Means the error term in one period should be independent of the error term in the other period. If the consecutive error terms are found correlated, we have the problem of autocorrelation. Means that if the consecutive error terms are correlated, the error term in one period is correlated with the error term of the other period, then we have the problem of the autocorrelation. We can test the autocorrelation by using the Delbert-Watson test, DW test. This is the Delbert-Watson statistic, DW, which is usually denoted by small d. Yes, this is usually denoted by small d, DW statistic. The value of this Delbert-Watson statistic, this lies in the range of 0 and 4, and the ideal value is 2. If the d value is equal to this is small d, if this d value is equal to the 2, this means that there is no autocorrelation, otherwise there may be positive or negative autocorrelation. So this was something about the regression. So I hope you may have taken some of these points. See you in the next class. Thank you. Allah Hafiz.